Hi everyone, welcome back. This is Earth and Space Science 102. I'm Stephanie Welch, and we are going to continue on with lecture 10 of this course. So in this lecture, we're going to be kind of going from what we talked about in the last one. We're going to be continuing to talk about the sort of background information that you need to understand how and why things move in space. Now, all of the, even the ancient Greek scientists and the Renaissance scientists that we talked about in the last lecture are going to be relevant to what we're going to talk about today. But no one is going to be more relevant to the subject today than Isaac Newton, the final of the sort of Renaissance era scientists that we talked about in the last video. Now, in addition to inventing calculus, inventing this whole new branch of math, in addition to everything else that he contributed to our understanding of science and math, he allowed us to really begin to understand what holds the universe together and what gives the universe its structure, gravity. And he allowed us to come up with three laws of motion that would allow us to understand how things move in space. So that's really sort of where we're going to go today, where we're going to start off anyway. We're going to start off with this idea of gravity. Basically, if somebody asks you what gives the universe its overall structure, what holds the universe together, what is the fabric of the universe, the one-word answer that you could honestly give them is gravity. Really massive objects in space, and we're going to see the mathematical equation for this a little bit later on today, really massive objects in space are going to hold other objects in its sway. This would later be described by Einstein as a warping in the fabric of space and time, and larger objects creating a bigger depression in the fabric of space and time than smaller objects, and therefore we're always falling down into this fabric of space and time. Newton basically just referred to this as gravity. It's basically why things fall down on the surface of the Earth. If you're comparing an apple to the entirety of the mass of the Earth itself, then of course the Earth is going to be the more dominant of those two. It's going to pull the apple down from the tree. It's going to hold us to the surface of the planet Earth. When you look at it from the perspective of our entire solar system, our sun, at the almost the very center of the solar system, is going to account for 99.9% of the mass of the total solar system. So of course, all of these little piddly planets, including the ones that we're on, they're all going to be held in sway by that massive object, and we're stuck in orbit around those objects. We can even look further out than that. We can look at the orbit of our entire solar system around the center of mass of the Milky Way galaxy. And we know that whatever is there at the center of the Milky Way galaxy is the mass of 20 million suns. So the more mass you have, the more sway you have in terms of gravity, and gravity is going to hold the universe together, basically give it its overall structure. Everybody that we talked about prior to talking about Newton, Galileo, Copernicus, Ptolemy, all of these other scientists really had no understanding of what was actually holding together the universe. And so everything that has happened up to the point where gravity began to be understood is just steps towards this really, really big understanding of what's actually holding the universe together. So while all of these other people did really, really important things to solidify the idea that the solar system was sun-centered, they didn't have a way of explaining why that was. Gravity and Newton would allow us to figure out exactly why that was. All right, so in Principia, his dominant work, Newton would publish, along with many, many other things, the three laws of motion. And the way that I like to go about talking and teaching about science and physics and the universe is to frame it around these three laws of motion, not to be confused with Kepler's three laws of planetary motion. These are Newton's three laws of motion that apply anywhere. They apply on the surface of the Earth, they apply in the universe, and they allow us to understand the motion of objects. So we'll be talking about other things along the way, but it's really important to remember that we're kind of couching this, we're outlining this around Newton's laws of motion. Now, hopefully at this point, you're sort of going about in your head, kind of rewinding back to maybe ninth grade and going, okay, what were Newton's 3 laws of motion? There was F equals ma, there was something else, da, 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 da. So let's first start by reminding ourselves what the 3 laws of motion actually are. These are Newton's 3 laws of motion that apply on Earth, as in the universe, as in anywhere. The first law is simplified in one word as inertia. An object in motion stays in motion, an object at rest stays at rest. The foundation of the idea of inertia would actually come from Galileo. The second law of motion is essentially just F equals ma, that a force is equivalent to an object's mass times its acceleration. And in addition to inertia, we'll be talking about F equals ma in a little bit more detail. The third is every action has an equal and opposite reaction. If you jump up, the gravity brings you back down. If you hit a wall, your arm's going to hurt because the wall hits you back, and so on. So all of these are incredibly relevant to understanding almost anything in the universe. And everything that we're going to be talking about is going to be couched around these 3 laws of motion. So we'll start with the first one. Simplified in one word is inertia. Galileo established the idea of inertia to sort of alleviate some of the fears that people had of trying to understand how Earth could possibly be in orbit, how Earth could possibly be moving around the sun. So one of the great fears that people had was, okay, so let's say you have Earth and it's actually not stationary. It's not the center of the universe, but it's actually in motion and it orbits and rotates around the sun. Shouldn't we just fly off the Earth? Isn't there, won't we just become detached? If Earth is moving through space, do birds and clouds in the sky just get left behind as the Earth is moving around? So these were actual fears that people had at the time, that, the Earth couldn't possibly be in motion, because if it were, we'd have all these other problems. Galileo basically established, or began to establish, and it would later be sort of solidified by Newton, that objects can move with a moving Earth, partially due to gravity and partially due to the object having inertia. So as you have an object moving in space, it's going to continue to move in space unless something is going to stop it. Now, it's really difficult to think about an object and its inertia on the surface of the planet, because on Earth we have all of these other forces that work in opposition to an object's inertia that are invisible, but they do slow objects down. So inertia would become Newton's first law of motion. A body in motion stays in motion, but that's really hard to show on the surface of the planet. Okay, take for instance the example, if you're on the interstate and you're going 70 miles an hour in your car, you know that if you take your foot off the accelerator that you're going to slow down. So you're actually losing inertia, you're slowing down. But there's a reason for that. If you were in your car, and let's say your car was airproof and we get rid of all the other complexities, and that car was just moving through space, if it were moving at 70 miles per hour, it would continue to move at 70 miles per hour forever without any need for any sort of external force unless something acted to slow it down. On the surface of the Earth, that car experiences a frictional force with the surface of the planet of the Earth. The planet Earth, that frictional force is an equal but opposite reactionary force that slows the car down. If you have if you have an airplane and it's moving through the Earth's atmosphere, then it has to, just like the car, have a continued source of thrust to continue to move it through the atmosphere, because it's experiencing friction with the actual gas molecules in the Earth's atmosphere. Without that continued source of thrust, it too slows down, crashes down to the surface. So on Earth, we have all of these messy external forces that you have to deal with to understand anything like this. It's actually simpler to understand inertia in space because there's no outside, there are few outside forces to have to deal with. And just the vacuum of empty space, completely devoid from the gravity of any other object, an object in motion really does stay in motion. So this allows us to begin to understand orbital motion, why an object is stuck in a loop around another object. An object in motion, once you start an object's motion going without some external force that's going to change the object's motion, that object will remain in motion forever, for billions of years, for the entire duration of the lifespan of the universe itself. An object can remain in motion. So if you're in your spacecraft, if you're in a Starship Enterprise and you're going at exactly 1 light year per second, you're going to continue to move at that speed forever and ever and ever and ever unless some force acts to slow it down. Now, the course of the planets, the motion of the planets, was set into motion long, long ago with the birth of our solar system. We think that our solar system formed some 4.5 billion years ago, and the motion of all of the planets, all moving around in the same direction in our solar system, was set into motion at that time. They're still going along for the ride. They still maintain their original inertia, and they will continue to move at the same rate, in the same direction, forever and ever and ever, because they continue to have inertia. Now, if you're dealing with a curved path, like an orbit, instead of an object moving in a straight line, then there has to be some other force at play, something else that's going to be controlling the object's motion. And that force, in terms of orbiting planets in our solar system, is gravity. Not only do we have inertia, we're constantly moving in a straight line, we're also constantly, in a sense, sort of falling into the sun. We're being held on a rope, a short leash to the sun, and that leash is essentially gravity. So we move at the same rate indefinitely, except we move in a circular path, or nearly circular path, as Kepler proved, around the sun. And we do this indefinitely for years, for billions of years into the future. So one way of describing this, one way of trying to figure out how you get an object in orbit around another object, is to think of launching some object off of the surface of the Earth to get it outside of the Earth's atmosphere. If it's stuck in the Earth's atmosphere, then it experiences frictional drag, and then it's kind of useless to this example because it's going to lose orbital energy, come crashing down to the surface of the Earth. But if you could fire a cannon or throw a baseball so hard that it actually left the Earth's atmosphere and started to go out into space, then there would be two forces at work that control its motion: the original speed in which the object was moving and the gravity of the object that other object, the baseball or the cannon, was moving around. So let's say you fired that cannon out away from the surface of the Earth. It got outside of the effect of the Earth's atmosphere. Then that object would maintain its original speed and move around the Earth. It's still stuck. It's still held to the Earth by that leash, by gravity, but it moves indefinitely because it has inertia. So inertia allows us to understand how things end up in orbit and why they continue to move in orbit. And that, in a large sense, is all that the universe is a whole myriad of objects like asteroids, comets, planets, moons, stars, all in orbit around bigger things, all stuck in their paths for billions and billions of years, unless something comes along to change things up, to shake things up. So that's going to be sort of our example, if you will, or sort of our way of thinking about Newton's first law of motion, inertia. Inertia gives us orbital motion. The second of Newton's laws is going to be that F equals ma. But in order to really understand it, we need to kind of detangle it a little bit and talk about some of those individual terms. In order to talk about acceleration, one of the variables, you have to first understand how we describe motion. Now, motion can be described by the speed in which the object is moving. It's just a rate. It's just a distance over time. So motion is a speed, or if you prefer a velocity, we can talk about it in terms of it moving at a constant speed. A constant speed is essentially a velocity. The only difference between velocity and speed, by the way, is a velocity is a vector quantity. So it includes a direction as well as a rate. Speed is a scalar quantity. Take, for instance, you could just say, in order to get to Baton Rouge from Hammond, you get on the interstate and go 70 miles per hour. That's not enough to actually get you to Baton Rouge. It's a scalar quantity. That's just telling you how fast you need to drive. In order to get you to Baton Rouge, you'd need to tell somebody to get on I-12 and go west. That west part of it makes it a velocity instead of a speed. Okay, so that's velocity. That's one of these terms. And you need to understand velocity before you can understand what an acceleration is. Acceleration is any change, positive or negative, to a velocity. If you increase or decrease your speed, then that is called an acceleration, a change in velocity. Now, the thing that's actually going to cause gravity to work is the acceleration due to gravity, which is going to be dependent upon mass. The acceleration due to gravity on the surface of the Earth is 9.8 meters per second squared. That's essentially how much change in velocity is occurring as you have an object that's approaching the surface of the Earth. So that's one of the two things that we need. The other is what mass actually is. Mass is really easy to confuse with weight. We almost kind of refer to those things interchangeably on the surface of the Earth. And as long as you are on the surface of the Earth, they practically are interchangeable. Your mass versus your weight is going to be the same unless you're changing your reference point. So while mass is not going to change, mass is something that's going to be no different here than it is on the moon or it is in free fall or on Jupiter, weight is going to change because weight is actually a force. Now, your mass doesn't change between either of these locations, but your weight actually does because your weight is a force. It's your mass times the acceleration due to gravity. So the idea that, for instance, you're weightless in free fall. If you jump out of an airplane and forget to pull your parachute string, then you're going to actually be weightless. It doesn't mean that all of your mass just goes away. It just means that while you're in free fall, you wouldn't actually register anything on a scale because your weight is a force. It's the force that would be pushing down on that scale that is your mass times the acceleration due to gravity. Because the moon, for instance, is only 1% of the mass of Earth, then the force due to gravity on the moon is very, very, very small compared to on Earth. But the mass would be the same on either place. So mass is really, if you peel back all the layers, mass is the main sort of underlying thing that is going to control gravity. The mass of the moon, for instance, being 1% of the mass of Earth means that the moon has a much smaller gravitational pull. The moon's basically stuck in orbit around Earth instead of the other way around for that reason. The reason why the sun is the main driver of all of the motion of all the other objects within our solar system is because it's by far the most massive object. So that gives us all the background that we need. It gives us how to understand motion, how to understand mass, to understand what a force is, and to understand the force due to gravity, the most important of all of the forces that you could apply to Newton's second law of motion. So underneath all of the vocabulary and all of the words, Newton's second law of motion is just really 3 letters. F equals ma. F stands for a force. One unit that you could use is a Newton, or a kilogram meter per second squared. And that is a combination of the 2 variables that you need to calculate a force. M, which stands for mass, possibly in kilograms or some other unit. A, acceleration, meters per second squared, or any sort of distance over time squared. So weight is a force. Weight is a force that is a mass times the acceleration due to gravity. On Earth, that acceleration is 9.8 meters per second squared. And there are many other forces at work in the universe, and the forces are going to be the thing that could potentially change an object's inertia. Take, for instance, a frictional force as your car drives down the road, and that car slows down when you take your foot off the accelerator. It's because there's that equal but opposite reactionary force slowing you down. It's a push in the other direction. Another thing that you sort of need in order to understand gravity is not just this equation that only gives us a single force, but an equation that gives us the force between any two objects in space. And in addition to F equals ma, Newton also gave us this second law, the law of universal gravitation. So this is another way of calculating a force. In this case, it's the force due to gravity between any two objects. And so it gives you everything that you need in this equation in order to understand the total force due to gravity between any two objects. Those two objects could be the Earth and the Moon, the Earth and you, the Earth and the Sun in the center of the Milky Way galaxy. Anything that you want. If you have all of these variables, you can calculate the force between any of those two objects. Now, the first thing that you need is the mass of both of these objects. So if the example is you and the Earth, you would need the mass of you and, of course, the mass of the Earth. And believe it or not, that's something that's actually calculable. You don't need to be able to take the Earth and put it on a scale to be able to determine its mass. All you really need is an understanding of the way that objects move around the Earth. Like, take, for instance, the Moon orbiting around the Earth in order to get an idea, or at least an estimate of the Earth's mass. So if you were one of these objects, one of the M's, and the other M was the Earth, then one would be so far outweighed by the other, one of those, it would be so small and the other one would be so big that it's basically just sort of negligible. And then you could talk about an object's surface gravity. And that's what we're going to deal with in the sort of some upcoming slides here. So instead, let's look at this from the perspective of two bigger objects. Let's make the little m, this blue sphere, the Earth, and the big yellow m, the Sun. These are two objects, still with one being much larger than the other, but they're on somewhat of an equal footing at this point. So you need the mass of both of those objects in order to calculate the force due to gravity. And you need the distance between the two. And those are the only variables in this equation at all. The only other letter in this equation is that big G, which is a gravitational constant. And constants are great in science because it's basically just a number that's there to make the math work out. It's one that's not going to change between one running of this equation and the next. So it's just a number that you stick in to make this work. If you have that constant, and if you have the variables, the mass of either object and the distance between the two, then you can calculate the force due to gravity. If you're dealing with surface gravity, then you might be dealing with the radius of the object, like the radius of Earth, instead of the total distance between the two. So that's why it's an R instead of a D, but you could basically put radius, distance, they're interchangeable. Now, the really important thing from our perspective, I know as soon as I put an equation up that everybody's thinking, okay, I'm going to have to be able to throw some numbers in this equation to actually calculate the force of gravity. What I'm always concerned with is that you know what the variables are and how those variables affect the outcome. What this really means is that whenever you increase the mass of either object that you're talking about, if you go from talking about the gravitational relationship between the Earth and you to the Earth and the Sun, then that's going to greatly increase the overall force of gravity. So we would say that the force of gravity and mass have this proportional relationship. If you increase one, then you increase the other. If you increase the distance, and the variable that we use for that distance is sometimes r, sometimes d, if you increase the distance between any two objects, of course the force of gravity decreases. So even though when you're talking about the relationship between the Earth and the Sun versus the Earth and you, you're dealing with a much greater distance between the Earth and the Sun, the force due to gravity, the total force due to gravity is actually much greater between the Earth and the Sun because you're dealing with a much greater mass. So you always have to be thinking about these two opposing forces. The distance and the force of gravity are going to have an inverse relationship. As you increase the distance, you decrease the force of gravity. As you increase the mass, you increase the force of gravity. They have a positive relationship. All right, so that's basically sort of talking about forces. It's talking about gravity. That's all applicable to Newton's second law of motion. The final law of motion that we're going to talk about is the action-reaction law. In Newton's third law of motion, it states that when you have two objects interacting, they create equal and opposite reactionary forces on each other. If you jump up off the surface of the Earth, gravity pulls you down. That's an equal but opposite reaction. If you're driving down the road, you ultimately slow down because there's a frictional force slowing you down. It's a force in the opposite direction. So all of these reactionary forces tend to sort of balance out the universe and give, again, the universe a lot of its structure. Surface gravity is going to be related to this third law of motion. In surface gravity, you have really only one mass to speak of, one mass that's particularly important, and that's the mass of the object that you happen to be on. The force of force due to gravity of the Earth, the mass of the Earth so far outweighs the mass of any individual person on its surface that that small m in the universal law of gravitation basically just sort of goes away altogether, and you could be talking about its surface gravity. So the surface gravity of an object does far more than just hold objects to its surface. It actually influences the overall size of the object and whether or not an object is able to retain an atmosphere. So we're going to look at how surface gravity actually influences an object's shape. First thing that you have to understand is that the vast majority of all objects in space, especially really massive objects, happen to be spherical. So you don't have triangular, square objects. You don't have really strangely shaped objects in space for the most part. They're either really small objects like asteroids and comets that might be sort of oblong in shape, or they're bigger, more massive objects that happen to be round or spherical. Stars are spherical. As much as we like to draw stars as 5 or 6 pointed figures on a sheet of paper, the only reason we draw them that way is because sometimes from any point of light, as that light enters into our eye, some of that light gets diffracted and we see that object as a pointed structure. But in reality, stars are spheres. They are balls of gas in space. Planets, for the most part, especially bigger planets, are almost perfectly spherical. So all of these objects are mainly spherical, and the reason for that is because a sphere is going to be, in terms of gravity, the perfect way of creating an object that has the same gravity no matter where you are on the object's surface. Gravity is constantly pulling an object towards the very, very center. And if an object is massive enough, its overall shape can be defined by gravity into this perfect gravitational shape, which is a sphere. So gravity tends to pull objects into a sphere, especially towards the formation of an object. Take, for instance, the formation of Earth. When the Earth originally formed, it was a lot hotter and much more pliable than it is today. It was largely in a molten state. And we think that gravity pulled all of that melt into a particular configuration, with the heaviest material at the center, the lightest material at the surface, and an overall spherical shape. Less massive objects in space, like asteroids, tend to not be spherical because they don't have enough mass to have enough self-gravity to become spherical. So in this side-by-side picture, you can see a small asteroid versus a large planet like Earth, and you can see the difference in the shape of these two objects. The small, less massive object, the asteroid, is oblong in shape, kind of potato-shaped, very heavily cratered. The Earth, in comparison, is almost a perfect sphere. So the reason why we have spherical objects in space, you can attribute back to gravity. The other thing that you can attribute back to gravity, back in a certain way to Newton's third law of motion, is this concept of an object having a certain escape velocity. And that escape velocity actually influences the planet's ability to retain an atmosphere and the composition of the planet's atmosphere. So one way of thinking about this is in order to escape a planet's orbit, in order to completely get away from the gravitational pull of a planet or any object like a star, like our sun, you have to be going at a particular speed that's going to be determined largely by the object's mass and its size, or r, its radius. You have to be going at the object's escape velocity. The escape velocity of Earth is 11.2 kilometers per second. It doesn't sound like that fast a speed, but because you're dealing with kilometers per second, you're dealing with a speed that's far, far greater than the speed of sound. This is at least about 4 or 5 times the speed of sound. That's how fast you have to be moving to actually escape the gravitational pull of a planet like Earth. So escape velocity, I've got the equation down here at the bottom of the slide here, can be defined as the square root of 2, the gravitational constant, so just a number that we're sticking in there to make the math work, the mass divided by the radius. Because again, the mass is on top of this equation, it has a positive relationship with the escape velocity. The greater the mass, the greater the escape velocity, the greater the speed in which you have to be going to escape the object. The number on the bottom here, the radius, is basically a way of saying the size of the object. If you have a really, really big object, that means it actually is going to allow you to move slower to get away from it because it has an inverse relationship with escape velocity. Now, this, believe it or not, actually has an impact on the composition of a planet's atmosphere and the ability of an object to actually retain an atmosphere. So in addition to controlling sort of, let's say, how fast you have to be shooting a cannon out into space to actually have that cannonball leave the gravitational pull of the planet, it also influences what kind of an atmosphere a planet is able to retain. So in thinking about these solid objects like a cannonball actually leaving Earth, you have to be thinking about this object moving at a particular speed. When we look at the temperature of a gas, that temperature is really just a manifestation of all the average kinetic energy of all the particles that make up a substance. We talked about that way back at the beginning of the class when we did weather and climate. When you think about the temperature being really cold, all that is a slow speed in which the particles of gas are moving in a room. If the temperature is warmer, that means those particles are moving at a faster speed. So all that we're dealing with on planet Earth in terms of the composition of our atmosphere is a whole bunch of particles that are moving at a particular speed. And that speed is determined by the temperature and also by the composition of that gas. Heavier gases tend to move slower, and really lightweight gases move much, much faster. In addition to that composition being the determining factor, it's also temperature that's the determining factor in which all of those particles move. In the range of temperatures we have on Earth, and given the escape velocity of Earth, Earth is capable of maintaining only an atmosphere that has a certain composition, a composition that's mainly based on heavier and less common gases in the universe. So here I'm going to chart out, and this might be a little bit more of a difficult way of thinking about this than the next way, so stay tuned for me. But I have sort of charted out here the escape velocity of several different planets and other objects within our solar system, and the typical speed in which certain types of gases are going to move, namely nitrogen, carbon dioxide, and hydrogen. So the whole y-axis of this graph you have to think of as not only the speed in which these gases are going to move that are plotted out on this graph, but the escape velocity of these planets. And while planets like Jupiter and Saturn are larger in size and their greater radius should actually be detracting from their escape velocity, they're also many, many, many times more massive than a planet like Earth. So their overall escape velocity is actually much larger than a planet like Earth. So all of those planets at the top, Jupiter, Saturn, Uranus, Neptune, those are the gas giant planets, the Jovian planets of our solar system. And they all have very, very thick hydrogen and helium rich atmospheres simply because those planets are massive enough to hold on to gases like hydrogen and helium. The cutoff for the hydrogen gas being able to be retained by a planet is that first of the dashed lines on that graph. Below that dashed line, you have planets with a lower overall escape velocity, meaning a limited capacity to hold on to gases like hydrogen and helium. So Earth, Venus, Mars, Mercury all fall well below that line and therefore can't hold on to gases like hydrogen and helium. Hydrogen and helium are far, far more common in the universe and make up for thicker atmospheres on those gas giant planets. Our inability to hold on to gases like this is why we have thinner atmospheres on planets like Earth. We can, however, hold on to gases like nitrogen, oxygen, carbon dioxide, water vapor, and then those become the dominant gases in our atmosphere. Then as you go all the way down towards the bottom where you see Mercury and the Moon, those are objects in space that have such a small escape velocity because their mass is so small that they can't hold on to almost any of the common gases. Certainly not nitrogen or carbon dioxide. They can maybe hold on to trace amounts of xenon. So those planets don't even really have atmospheres. They are completely devoid of any kind of atmospheric envelope around the planet. So another way of thinking about this that is a little less sort of graphical and more example based is to just give you sort of three objects. In these three objects, we've got the smallest and least massive object, an asteroid. The medium-sized object, Earth, and then the large object, the planet Jupiter. And in this example, with an increase in size also comes an increase in mass. So the overall effect this has on escape velocity is that these bigger planets that are more massive are going to have a greater escape velocity. So on our first hypothetical object, the asteroid, we have a small object, much like Mercury, the Moon, comets, most of the comets in our solar system. These are all going to be objects that are going to be so small that they don't have a high enough escape velocity to hold on to almost any gas molecules. So those gas molecules are therefore moving faster than the escape velocity. They vacate the surface of that object. There's no atmosphere surrounding most asteroids and most small objects like the Moon and the planet Mercury. Sometimes when you get way out into the outer solar system, you're dealing with planets that are so cold that those gases move slower. So on the planet Pluto, for instance, or should I say the dwarf planet Pluto, that planet can actually hold on to small amounts of nitrogen in its atmosphere, simply because the gas is too cold to move faster. In a medium-sized object, like Earth, you're dealing with an object that has a greater escape velocity and therefore a slightly higher ability to hold on to gas molecules. It means it can hold on to some gases, but not all of them. It can hold on to heavier gases that just move slower under the range of temperatures that you have in the Earth's atmosphere. So that means you end up with an atmosphere that's almost entirely comprised of gases that were released when the planet formed in the first place. So what that ultimately ends up meaning is that our planet's atmosphere has nitrogen, oxygen, carbon dioxide, and other planets that are under the same range of temperatures and have the same or similar mass of Earth are going to have similar compositions of their atmospheres. Large objects, so those are going to be the so-called gas giants, the Jovian planets like Jupiter and Saturn, Uranus, Neptune, the Sun, all stars, all really, really massive objects in the solar system, are going to have the highest escape velocities, and therefore they can hold on to any gas at almost any temperature. And that means that those gases, even at really high temperatures that you get in the Sun, are still gravitationally bound to those objects. And because hydrogen and helium make up 98% of the universe, these become even more massive by virtue of being able to retain large atmospheres. For this reason, Jupiter became 318 times the mass of Earth. If you look at its core, the thing that actually attracted all of those gases to the surface to begin with, it only started out about maybe 10 times the mass of Earth, but just massive enough, we think, to retain large amounts of hydrogen and helium in its atmosphere. Now, the greatest example of all of escape velocity comes when you're dealing with an object that's incredibly small, but extremely massive. And these are almost science fiction sort of objects in space that we know very little about, called black holes. A black hole is an object that is as small as the tip of my finger, as small as an individual atom. So its radius is extremely small. That means that that radius is not going to have a large effect on the escape velocity. But black holes, or the singularity at the center of a black hole, actually has an incredible amount of mass, sometimes millions or even billions of times the mass of our sun. So the escape velocity of an object like that is almost off the charts. It's almost incalculable. The escape velocity of these objects are actually greater than the speed in which light travels. And light travels at 300,000 kilometers per second. So if light can't escape it, then we don't really see these objects at all, and therefore they become black holes. So I thought that would just be sort of a cool way to end off the subject of escape velocity. Escape velocity, of course, is going to be sort of an example, a manifestation, if you will, of Newton's third law of motion. That's going to wrap up for today our whole discussion on Newton's three laws of motion and the little sort of bit of background physics that we need before we can start on understanding our solar system. So the next thing that we have to talk about is a bit of a survey of our solar system. We're going to go object by object and look at all of these as individual objects. And then I think much more exciting is going to be our way of looking at all of these objects in conjunction with how the entire solar system actually formed. By the end of the next two class periods, we'll actually have, I think, a working understanding of how our solar system, how our planet, how everything fairly close to us in the universe came to be. So it's really exciting stuff. I'm looking forward to it. And until next time, keep looking up.